Hello, and welcome to my talk on using first principles DFT plus U+J algorithms to model transition metal oxides. The issue at hand that we are trying to solve with this research is that density functional theory methods such as PBE and LDA, while being quite fast, are quite bad at describing the band gaps of oxides and semiconductors in general. Now, you can correct this sort of with hybrid functionals, but that costs a lot more computational time. A much cheaper option is to incorporate corrections to add on to the energy, such as Hubbard's U and Hund's J. However, this is often either inaccurate or it distorts the geometry, or you have to pick a value that is tuned to your empirical value, to the value that you want, which hampers your ability to discover new material band gaps, and is not broadly applicable in between different papers and so on. So we want a first principles simple methodology that will get you accurate band gaps from first principles. So the most common methodology used to do first principles U and J corrections is the linear response method of Coccaccioni et al. So this involves you pick a subspace, you apply a perturbation to it, and then you observe the effect on the total trace of your occupancies, both before and after it's screened by the surrounding electrons. You look at the slopes at several different perturbation values, and then from that you get your U correction value. You can do the same thing with J, as other researchers have found out. It's only slightly different in that you're applying different perturbations to the up and spin up and spin down sections of your orbital. But other than that, you get it's the same thing. You get the difference in slopes gets you the J correction. And in fact, you can go even further than that. You can, for a non-spin polarized system, you can get the U and the J all in one by just applying a perturbation to the spin up, and then using all the parameters in there gets you U and J at the same time. So the full procedure is to converge a unit cell of the material. And in this case, we picked 5 different materials that are non-magnetic oxides, represent a wide range of different structures and places on the periodic table. And once you got your material, you zoom it out, get a large supercell, you pick one atom to apply, one orbital from that atom to apply your perturbations to, and then you measure the change in occupancies and follow the procedure I showed you in the previous slide, gets you U and J parameters. And then you go back to the unit cell, and you get the unit cell, you apply the U and J, and then from that we calculate, the band structures, bond geometries, band gaps, etc., and compare it against the usual values from the literature. So we start with, so our results start with titanium dioxide in the rutile form. And you can see these are several different methodologies we tried. So starting with regular PBE, no corrections, you see there's a massive underestimate. You're at -1.8, it should be 3. And if you apply U to just the titanium atom, it doesn't help much. You're doing a slight increase. But then if you do to the titanium and the oxygen at the same time, you overshoot. You go up to 3.8, which is too much. Now, one method of applying J brings us down. This is the effective U, where you just subtract the J from the U value. So that works all right. But the best methodology, which we call DFT+U+J, you implement the U and J separately as separate corrections, which you can do in Quantum Espresso and in a few other packages. And this is about as accurate as hybrid functionals. So the next question is, does this distort the geometry? And the answer is no. Actually, the PBE and the DFT+U+J have about the same volumetric error. The only thing which is distortion is if you put the U on the titanium but not the oxygen atom. Does it distort the band structure? Nope, not really either. If you look at it, you can visually see that they're pretty much the same, and that's reflected in effective mass values. So zirconium is pretty much the same story. No change from U on the zirconium only, put the U on both of them, it shoots up. And then when you put the DFT plus U plus J, it actually hits pretty much exactly within the range of experimental error. So this is the sweet spot for our methodology. We get it like exactly right. And yeah, again, no change in geometry, no change in band structure. Well, okay, so the only change in band structure is that the valence bandwidth gets a bit thicker with our methodology. Yeah, apart from that, not like big changes. So go again to hafnium oxide. I'll just speed up as I go along because it's pretty much the same story. Yeah, just jumping up. So in this case, yeah, we get nearly the right answer, but we're now overestimating the band gap. So we're not quite as good as hybrids for this material. But again, no geometric distortion. Again, the only thing that's different is the valence bandwidth in the band structure. Cuprous oxide, same deal, not quite as good. We're underestimating at this point. So we seem to either, so the small errors we do have seem to be like either up or down. It's not systematic in one way or the other. We do seem to be introducing a second gap into the valence bandwidth. Not sure how physical that is. There's like a limited, but apart from that, it's pretty similar. There doesn't seem to be any distortion or other like negative aspects of this methodology. Now for zinc oxide, this is a material that a lot of people have had a lot of problem with linear response calculations for. And yeah, we encountered similar difficulties. The linear response doesn't seem to work for 3D orbitals of zinc. It blows up. It's either numerically inaccurate or you get huge values. We were sort of able to get a U calculated, but the band gap, the result was like huge U values, which were huge overestimates of, well, 3 eV overestimates of the band gap. So one of the reasons we identified was, I mean, if you look at the like actual character near the band edges, the d orbitals don't actually make a huge difference to the band edges. So we look particularly at the conduction band, like, well, hang on, what if we switch to s orbitals? And if you do switch to applying to the zinc s orbitals instead of the d orbitals, you actually get like it's smoothly behaved, you get reasonable U values, and the results match up pretty well. So here are the results. Yeah, you can see we're about like 0.4 eV over, which is better than HSE06 and so on. So yeah, it gets a reasonable value for the band gap. Does this crazy business with the zinc doesn't really affect the geometry. In fact, it greatly reduces the error. We're much better than regular PPE. Again, we've opened up the second gap, which is already typical, but that there is some experimental evidence for some gap, although it's a little too high here. But apart from that, yeah, everything's pretty normal in the zinc oxide case. So we can take a final comparison here. Can look at all of the materials all together, can find that a few trends going on. So regular PBE always underestimates, has a pretty big error. If you just apply the U to the metal atom, it does not help particular much. It's like a very slight change, not very helpful. If you do it to all the atoms, so the metal and the oxygen, you overshoot, you go the other direction, you're now overestimating and you're still quite wrong. So the final result of DFT plus U plus J is extremely accurate, about as accurate as hybrid functionals are over the test set we considered. So yeah, this methodology gets you pretty much the right band gap at a fraction of the computational cost of the equivalent hybrid functionals. And the geometric distortion is not really present. It's only if you look across all the materials, the only thing with distortion is if you put your U value on just the metal. As soon as you balance it out with the oxygen, everything's fine. So in summary, we tested DFT plus U plus J on a wide variety of different materials. representing lots of different areas. Using a simple linear response method, it's quite easy to use. You're just looking at occupancies before and after. It's a few simple scripts. And then it's a first principles method. You can use it for anything. Gets you band gaps about as accurate as hybrid functionals. So apart from the hiccup with zinc oxide, it's like quite simple, quite easy, and gets you good results. Yeah, yeah. So the preprint is available on Arxiv. You can take a screenshot if you want to take a look at it. It'll be published. It's under review at PRR, I think. But yeah, so on to questions.